Welcome back. We mentioned on numerous occasions that PD models must be easy to understand and interpret. Basically, all kinds of people, even with a background in arts, should be able to understand and apply them. This is why PD models are often turned into simplified model versions called scorecards. Applying a scorecard is just like applying the PD model itself. A scorecard tool produces an individual creditworthiness assessment that directly corresponds to a specific probability of default. Because these creditworthiness assessments are named after the scorecard, they are called credit scores. In this lecture, we are going to create a scorecard based on our PD model. We store the coefficients of our PD model in a data frame called summary table. It contains regression coefficients for all independent dummy variables, except for the reference categories. As you can recall, we were not allowed to include the reference categories when estimating the model. However, when using it to predict probability of default, we just take those as zeros. Now, when creating a scorecard, we want it to be as interpretable as possible. Thus, let's include these reference categories and show them in the scorecard. We have a list of the reference categories here. Let's create a data frame based on it called df ref categories and call the first column feature name, just like the first column of the summary table. Then, assuming that there are regression coefficients for the reference categories and that they are all zeros, we can create a column coefficients with 0 values. For full consistency, I'll include a column with corresponding p-values with nan values. Now this data frame has the exact same layout as the summary table data frame. We'll store the scorecard in df scorecard. Then we'll merge the rows of the two data frames and reset the index. This way, we'll get the input from our PD model as if the reference categories were included in the model estimation and had coefficients of 0. Now let's make sure we have the name of the original independent variables as well. We are going to need it soon. We can save it in a new column called Original Feature Name. Note how we created the names of the dummy variables. First, there is the name of the original independent variable, then a colon, and then the respective category. So the name of the original independent variable can be found in the name of the dummy variable. It is everything before the colon. This is exactly how we are going to extract it. It equals the name of the original variable, dot string, dot split, and colon as a separator. Also, we need to specify we need the first thing returned by this expression, which is why we put 0 in brackets here. The index of the first thing returned by this expression will always be the name of the original independent variable. Great. Now the last column of this data frame contains the name of the original independent variable. Good job. Time for the real work. In order to create a scorecard, we need to turn the regression coefficients from our PD model into simple scores. First, we must decide what scorecard do we want to create. Let's say we want the minimum score to be 300 and the maximum score to be 850, just like the most typical FICO score. It will be useful to store these values in two variables. Let's call them minimum score and maximum score. Second, we must rescale the creditworthiness assessment produced by our model to the desired credit score. To achieve that, apart from the range of the scorecard, we also need the minimum and the maximum of the creditworthiness assessments that can be obtained from the PD model. Recall how we calculated PD for an observation. Each observation falls into only one dummy category of each original independent variable. Moreover, higher coefficients correspond to being a better borrower, that is, to better creditworthiness. So, theoretically speaking, the minimum creditworthiness assessment we can get from the PD model would be in the case where a borrower falls into all the categories of original independent variables with lowest model coefficients. Similarly, the maximum creditworthiness assessment we can get from the PD model would be in the case where a borrower falls into the categories of original independent variables with highest model coefficients. Well, let's find this minimum and this maximum. we have the names or the original independent variables in the original feature name column of our data frame. For each original independent variable, there is the same name here. Therefore, we can find the minimum values of coefficients for each group of rows that correspond to the same original independent variable. We do that by applying the group by method to our data frame. Then, we can specify that we want to group the rows by original feature name. Next, we should put the columns we want to aggregate. In this case, the coefficients column. Finally, we must specify how we want to aggregate. Let's start from the minimum. Great! Here we got the minimum per each original independent variable. Of course, the intercept in our model has only one value, so we got that value. Just as we intended when we were building the model, most minimum values are zeros. In a perfect world, that would happen here as well. However, when dealing with real data, that rarely happens. There are 3 exceptions, which are negative, but are very close to zero. Great! So the minimum possible creditworthiness assessment corresponds to the sum of getting all of these minimum values. Let's store it in a variable called minimum sum coefficients, and it's about minus 1.4923. Can you guess how to get the maximum possible values for a borrower on each original independent variable? Analogically, by grouping the same way and only changing the aggregate function to calculate the maximum instead of the minimum, then we can get the maximum possible creditworthiness assessment by summing these maximum values. Let's store it in a variable called maximum sum coefficients. Its value is about 5.6332. Now, how do we rescale the coefficients to scores? It isn't that hard. In order to turn each dummy variable coefficient to a corresponding score, we have to multiply each coefficient by the ratio of the difference between the maximum desired score and the minimum desired score, and the difference between the maximum sum of coefficients and the minimum sum of coefficients. Let's perform this calculation for all regression coefficients and store the results in the score calculation variable. Everything looks great, except for the very low value of the score calculation corresponding to the intercept. Well, that's because the intercept is not a dummy variable. It's a coefficient, which is always part of the calculation of creditworthiness assessment. That applies to every observation, regardless of the values of the dummy variables. In fact, the score corresponding to the intercept is very close to the minimum score an observation would get in the worst-case scenario credit-wise. So, what we want to see here is a value around our minimum desired score, which is 300. Actually, there is another equation that can help us to get the score corresponding to the intercept. Let's see what it is. First, we have to divide the difference between the coefficient for the intercept and the minimum sum of coefficients by the difference between the maximum sum of coefficients and the minimum sum of coefficients. This will place the coefficient for the intercept on a scale between 0 and 1, where 0 would correspond to the possible minimum and 1 to the possible maximum. Next, we must multiply them by the difference between the maximum desired score and the minimum desired score. Thus, the scale now becomes from 0 to the difference between the maximum and the minimum desired score. In our case, this difference would be 850 minus 300, so 550. Finally, to turn this into a number between the minimum desired score and the maximum desired score, we simply have to add the minimum desired score to it. So, let's see the first element of the score calculation column, that is, the element with index 0, to this expression and display the result. Alright, now we got about 311.87, which looks a lot more like what we expected. Now, the only thing left to do to get a simple, interpretable, and user-friendly credit scores is to round the score calculations we just performed. Conventionally, we prefer integer numbers. Let score preliminary be equal to score calculation with the round method applied to it. Great! Now let's check whether the minimum possible score and the maximum possible score are equal to the desired minimum and maximum scores. We can do that the same way we calculated the minimum and the maximum sums of regression coefficients. We group by original feature name. Take the minimum of score preliminary and take the sum of these minimum values. For the maximum possible score, we do the same. Take the maximum and take the sum of these maximum values. Well, the minimum possible score is 300, exactly equal to the minimum desired score. But as you may notice, the maximum possible score is 851. It's 1 point greater than the maximum desired score. This difference is due to the rounding we did. Can we fix it? Sure. We just need to subtract 1 from the score of every dummy category that yields maximum scores for each original independent variable. In other words, we could subtract 1 from grade A, home ownership mortgage, verification status verified, purpose credit card, and so on. However, it is best practice to subtract 1 from the variable that was, so to say, rounded the most. We can see that by calculating the difference between the rounded values in score preliminary and the values before rounding stored in score calculation. The greatest rounding has occurred where this difference is greatest amongst the variables giving maximum score. It seems that this is the variable, months since last delinquency, from 31 to 56. The score originally calculated for this variable is about 16.51. Then, this is rounded to 17, and there is a difference of about 0.49 between the rounded score and the original calculation, almost as high as it can be. So let's create a new variable, score final, equal to score preliminary. We'll leave everything else the same, except the value for variable months since last delinquency from 31 to 56, which has an index of 77. We'll, therefore, set the 77th element of score final to 16 instead of leaving it equal to 17. Okay, let's check again whether the minimum and the maximum possible scores are equal to the minimum and the maximum desired scores. Yes, this time the maximum possible score is exactly 850, precisely equal to the maximum desired score. There, our scorecard is ready, and the score final column contains the score for each category. In the next lecture, we are going to see how to use the scorecard to calculate credit score for a single borrower. See you there!